what you don't need to write down. It's completely up to you. So instead of using degrees, there is another way for us to measure an angle. Okay, radian measure is the measure of the arc length that is made up by two line segments that comprise an angle. So sometimes we need to describe a circle not in degrees, but we need to describe a portion of the circle, and we need a way to do that. So that's what radians enable us to do. So if you look at your calculator right now, it's probably in degree mode. And for the most part, we always leave our calculator in degree mode, no matter what we're doing. But going forward, we might actually change up the setting to degrees or radians, depending on the kind of question we're going to be solving. So what's a radian? Well, I quite like this little diagram here. Anybody like pie? A piece of pie? Nobody likes pie.
I like pie.
What kind of pie?
Coconut pie.
Coconut cream pie?
Yeah.
Yeah, it's pretty good. A friend of mine, what do you get somebody who has everything for their birthday? A coconut cream pie. Yep. So I was going to make her a coconut cream pie. I don't know. Is this Rebecca talking about pie?
Yeah.
Okay. Does someone in your house make it?
Yeah, my mom makes pie.
Is it a lot of work?
Yeah.
Okay, if you have a recipe that she would like to share, I'd love to have it, because I would like to be able to make a homemade pie for my friend, because she'd love it.
Okay, I will.
So if we're talking about pie, I think I'd rather have this sector down here. It's a bigger piece of pie. Okay, so if the angle is small, so if you look here at theta in the very first one. Okay, I'm looking at this angle right here. And if I compare it, those two angles are very different in size. The first one's a lot smaller than the second one. Well, the arc length that's across from that particular angle is small also in comparison to the arc length made for the bigger angle. So the larger the angle, the larger the arc length is. So this is an angle measured in degrees. Arc length is measured in radians. I can't measure this with a ruler because it's a curved surface. So I describe it as a portion of the whole circle. So for example, if this was 20 degrees, I wouldn't say the arc length is 20 degrees. I would say that as a fraction of the whole arc length of the circle. Can someone tell me if I continue this arc length all the way around? What's that called if I go all the way around a circle?
The circumference?
That's circumference. So the perimeter of a circle has a special name. It's the circumference. And if I know the radius, can I find the circumference? Well, I can. So we're going to talk about that also. So the radius is here in this black line, and it's this green line. So the radius, whether it's here or here, would you agree that they are the same length because it's the radius of the same circle? These would be the same also. Okay? Whatever they are, they would be congruent to each other. So theta represents an angle measure that's created by these two radii. So together, they make an opening. And as the opening gets bigger, the arc length gets bigger. So we do have a way to express arc length, and that's what we're going to talk about today. How many degrees are in a circle? 360?
Yeah.
How many degrees are in half a circle or semicircle?
180.
180, excellent. Okay, so we already know some formulas for circles, so we just talked about one of them. We talked about circumference. We also can talk about, and I think we've seen this guy, area, pi r squared. Okay? So the circumference of a circle can be expressed as 2 pi r, or it can be expressed as pi d. How do I decide which way to express it? Well, if I know the radius, I would use this one. And if I know the diameter, I would potentially use this one. It doesn't really matter. We'll get the same answer. So We can use the ratio of arc length to its radius as a measure of an angle size. So for example, in this diagram, what we have here is a sector. And what do all of these things mean, these little ticks here? What are all of these measures?
They're the same.
They're exactly the same. Good. So if we have our radius here, and we have our radius here, we know that they are the same length because it's the same radius for the same circle. So what we know is, though, if these are the same, if we take the arc length and we divide it by its radius, we should be able to get the measure of an angle. Well, in this case, the arc length is also the same size as the radius. So what's anything divided by itself?
1.
Good. So if this was 5, and this was 5, and this was 5, if I do the arc length divided by the radius, isn't the answer just 1? So we would describe that as 1 radian, if it's the same. Now you notice here, there's a little sign here. This little C, that means radians. So 1, if I do this, what does that say?
1 degree.
Perfect, yeah, 1 degree. So the nice thing is this. If you just write going forward, let's say you wrote down 1, and you didn't give me any units, I know that to mean 1 radian. So do you remember when we were doing some trigonometry previously, and if you didn't put degrees in, I would take a half point off. Not every time, but I would take it off probably once on the assessment. Well, this is why. Because if you gave your answer now as 30, I know that it's 30 radians because we don't actually have to write anything. Radians is always understood. So if your answer is in degrees, you really need to make sure that that degree symbol is there. Otherwise, I will think it's 1 radian. So here's another little example. If we have an arc length of 10 and a radius of 10, anything divided by itself is just 1. So you would end up with 1 radian. How are we doing? So if you have a sector, forgetting about the measurements for a minute, the degrees is in here. This is where degrees is. This is the arc length. The arc length is described in radians. The angle measure is described in degrees. So there's 2 different measurements for the same information given. Okay. So if we think of a circle, if we want to calculate the circumference, if I tell you the radius is 1, if I put 1 in for r, what is the circumference of the circle I'm talking about? Isn't it just 2 pi? I don't know what it is, but no matter how many times I adjust these, every time I close it and open it, they look different. It's fine. Okay, so the circle that we're going to talk about is called the unit circle, and it's called the unit circle because it's actually a 1 unit circle. So a 1 unit circle would have a radius of 1. And we're going to do all kinds of neat things with this circle. So, in the case of a complete circle, the ratio would be of arc length to the radius. So 2 pi r would be the full arc length of the circle, wouldn't it? 2 pi r. But I know the radius is what? Well, in our case, if the radius is 1, wouldn't I just be dividing by 1 and my answer would just be 2 pi? So the full arc length of a circle is 2 pi. That's the full distance around with a circle having a radius of 1. So a full revolution would be 2 pi radians. If I only rotated, though, halfway around the circle. Let's say I stopped right here. What would be the size of that arc length? If I start here and I rotate this way, the full way is 2 pi, so what if I go halfway? What would this be?
180.
In terms of radians though, 2 pi would now just be pi, wouldn't it? Because if I keep going all the way around, isn't this 0 pi where I start and 2 pi if I go all the way around? Okay? So it's worth remembering, it even says right here, that pi is actually the equivalent of 180 degrees. So do you see here they have 360 degrees is 2 pi radians. I can say 360 degrees is just equal to 2 pi. Radians is understood. I also don't need to put the radian sign here. I can say 180 degrees is equal to pi. So I'm not going to put pi radians here. I'm just going to call it pi. Radians is understood. Is there a question? It even says right here, in general, we'll leave off the symbol for radians, so any angle of pi radians is simply written as pi. So you don't need to put the little c in there is the moral of the story. But for 360 degrees, you have to put this symbol in. Do you remember when we worked with real numbers? Real numbers is often assumed, and then we just say if it isn't real numbers, if it's whole numbers or integers. So what's the big idea here? The circumference of a circle is 2 pi r. Okay, I don't know what's going on. I do have everything locked, so. Okay, so in higher math, only radian measure is used. It is more convenient and formulae using radian measure are usually simpler. So if you're going on in math, particularly pre-calculus and calculus, you're going to see radian measure a lot. Okay? So the fact that you're taking this course, even if you don't stay with IB, but you're doing the pre-cal route in calculus, you will benefit from this 100%. So if you look at this sector right here, I would name this arc AB. So the arc of AB is going to be this portion of the angle over, what's the total amount of degrees that we have in a circle? Isn't it 360? So for example, if I said to you, this doesn't quite make 90 degrees. Let's say theta was, I'm making this up, 70 degrees. If I have theta over the whole 360 degrees, whoops, sorry. Wouldn't that be 70 degrees over 360 degrees? So my arc length would be 7 over 36, would be the portion of the whole that I have. But to put it into radians, I actually have to multiply it by 2 pi r to put it into radians. So using degrees, we're talking about what degrees we have over the 360 total and then multiplying it by 2 pi r. Well, what's the radius of the circle we're talking about? We're talking about a radius of 1. So arc AB, if I actually look at what I have here, what happens to this little formula? 2 pi, what's 2 pi? Isn't that 360 degrees? So wouldn't these guys just cancel, only be left with, theta, r, or you can write it as r theta, it doesn't matter. So to find the arc length, that's what you would be doing. You would be multiplying the radius times theta. So the portion of the circle that we have is what I was trying to get at here. If I have 70 degrees, what portion is that? It's 7/36 of the whole circle. If we take a nicer one, like 90 degrees, if I say 90 degrees divided by 360 degrees, isn't that a quarter of a circle? Maybe that one's a little easier to get your head around. So what's the big idea? This is the big idea for this lesson. Radians to degrees and degrees to radians is what we're doing. So if you want to convert from degrees to radians, we're going to multiply by pi over 180. Could somebody also multiply by 2 pi over 360 if they wanted to? What does 2 pi over 360 reduce to? Isn't that 1 over 180 or pi over 180? Similarly here, if you want to change radians to degrees, you want to multiply by 180 over pi. Someone could also say, well, I'm comfortable with the relationship with 2 pi and 360, so I'll use this one. If I reduce 360 over 2 pi, don't I get 180 over pi? It's the same thing. What would be the advantage to using the pi over 180 and 180 over pi? Why would that be easier for me to do? What's smaller, 180 or 360?
180.
Right, so wouldn't it be easier for me to use this representation instead of this? It would be. Is this wrong? No, it just means you're working with larger numbers to do your calculation, that's all. Okay, so what would this look like in a question? I like the examples they give here because they give 4 different ones. 150 degrees for the first one says, we have to make that into radians in terms of pi. So we want the exact, we don't want any decimal places. So when you're calculating these, I would use the pi key on your calculator. Okay, so for A, we're going to take our 150 and we're going to multiply it by pi over 180. Do you notice they leave off the degree sign here? You can put it in if you want. Isn't it going to cancel out anyway? So what you get here is 150 degrees pi radians, whoa, lots of units here, over 180 degrees. Well, if I reduce 150 over 180, I think I get 5/6. So 5 pi over 6. Ivana, do you have your calculator there?
Yeah.
Okay, can you do a little calculation for me, please?
Yeah, sure.
Okay, so pi is 180 degrees. Can you multiply 5 times 180 and get your answer?
Okay.
And what did you get?
5 times 180?
Yep.
900.
900, and then we're going to divide that by 6.
Okay.
Did you get 150?
Yes.
Perfect. So, if you want to check your degree to radian calculation, can you just fill in 180 for pi and see if you get back to the degrees you started with? Good? Okay. Thank you for doing that. I appreciate it.
You're welcome.
In B, it says we have to go to radians also, but this time we need 3 significant figures. So I'm guessing we're getting a decimal. 131.8 is not a nice whole number. So 131.8, if I multiply that by pi over 180, so to get the radians to stay, you need to multiply by pi over 180. If you wanted radians to cancel when you're going with the other calculation, then you would just do 180 over pi. So, Ivana, do you have your, can you do this one more calculation for me, please?
Yeah.
Okay. I want you to do 131.8.
131. 0.8, yeah.
Yep, times pi. Get your answer. And then divide your answer by 180.
I'm not sure what my pi button is.
Okay.
So can I just
use 3.14 then, sure. So 131.8 times 3.14, get your answer. And then divide that by 180.
Okay. 2.29917.
So we're getting 0.30?
Yeah.
Perfect. So 3 significant figures. 1, 2, 3, we're good to go. Excellent. For C, we have to go from radians to degrees. Okay, well now I'm going to multiply by 180 over pi because I want to cancel out the radians and change it up to degrees. So basically what I'm doing is filling in 180 for pi and then dividing by 6 once I do the product. And D, we're going from radians to degrees, but the difference is this is approximate radians. So you're going to see something special happening with 150 degrees and 7 pi over 6 when we start talking about our unit circle. Okay? So to change this guy up, we're going to multiply also by 180 over pi. So if you have your calculator there, it might be a good idea for you to try this one. So essentially, you can just do, whoops. You can do 1.237 times 180, get your answer. And Ivana, if you're doing this or anybody else, you can't find the pi button on your calculator, you can just divide it by 3.14. That's fine too.
I found it.
You found it?
Yeah.
Okay, do you have to press, you might have to press second function, I think, to get it, do you?
Yeah, I have to press shift.
Okay.
And there's like an EXP.
Okay. I have to do that, I think, on mine also. So, in this case, though, the answer's in degrees. So you need to include that degree sign. If I don't put radians here, isn't it understood? I don't need it. It's assumed it's radians if you don't say anything. Okay, and we always report our answers in lowest terms. So I'm not going to leave 150 over 180. I'm going to make that 5/6. How are we doing? Pretty good?
I have a question.
Yeah.
Could you go, yeah. How do you know when to use 180 for pi and then when to actually use pi?
If you see pi and you're asked to go from radians to degrees, then 180 degrees would be substituted for pi.
Okay.
If you're asked to go from degrees to radians, you have to multiply it by pi over 180. So there's a nice little diagram right here in your book that when you're doing your notes, I would definitely write this down, this slide down, okay? Degree to radians. This is very helpful. Because if I'm going from degrees to radians, I have to figure out what portion of the circle do I have. So I multiply it by the ratio that I know that pi is for every 180 degrees. Does that help, Carly?
Yeah, thank you.
You're welcome. Please, if there are any questions, let me know, okay? That's why we're going through this together. Okay, so that's the first little section there. The second section is equally as short, okay? So I'm going to give you some questions to try where you're actually converting one to the other. So this is what I was talking about before, the unit circle. So today we're just going to get a little bit acquainted with it. We did talk about it a tiny bit when we were talking about how sine sometimes has two possible answers with the ambiguous case. Well, we're going to dive into this a little bit more so. So the first thing that we can recognize is this. Do you ever remember when you're doing the sine, cosine of a value, when you were doing trig questions with sine, cosine, tangent? every time you did cosine and sine, you always came up with a decimal most likely. A couple of times you might get 1 or -1 or 0, but more often than not, you would get a decimal answer. And the decimal answer would be between, I'll just call it x. It was always greater than or equal to -1, but less than or equal to +1. Every time. Well, cosine is your x and sine is your y. And again, I wouldn't get all hung up on this today because we're going to dive into it more so next class on Thursday. Your y value, the same thing though, should have always been a number between -1 and +1. And sadly, before now, we never talked to you about this. We save it for this unit. So think about the other grade 10s. It's really a shame that unless their teacher taught this outside of the curriculum, they're just getting their answers for x and y and not really knowing what they mean either. So, on your calculator, can someone take the cosine of 112 degrees and tell me what you get? I know it's going to be negative.
I got negative 0.3746.
Perfect. And that's rounded. Is it, Rebecca?
Yeah.
Okay. And then for the sine of 112, that should be positive, I believe.
Yeah, 0.9272.
1272?
0.9272.
Oh, 92. You did say 9. I'm sorry. And that's rounded. The last two is rounded appropriately, is it?
Yeah.
Okay, so as a little aside, thank you for that. I appreciate it. Over here, what's positive and what's negative for any coordinate in quadrant 1? Is it positive x and positive y? What about over here, quadrant 2?
Negative x and positive y.
Yeah, you guys already know so much about your unit circle, you don't even realize it. Down here, negative x, negative y. Yep, and what about over here?
Positive x and negative y.
Yes. So we're only just looking at the first one. Okay, so I just wanted to do this with you so that you're a little bit comfortable with what you're going to see. So keep in mind what's positive and what's negative and where. So when you actually did those calculations for sine and cosine questions previously, you were getting positive and negative values for those angle rotations because of where they are on your unit circle. Okay, which, I don't know, I think the unit circle is super cool. Okay, so don't be overwhelmed by the diagram. Let's just pick it apart together. So we can in fact use the unit circle to consider angles of any size. I like when we can kind of use things over and over that we know. So cosine is going to be your x coordinate of P. P is a point. That's all that P stands for. Sine is going to be the y coordinate. So we always start here at the coordinate 1, 0. Well, this is the center, and the radius of our circle is equal to 1 unit. Does it make sense that to go to this point, I'd go over 1, but I wouldn't go up or down? So what would the coordinates of this point be right here at the top? Well, I'm not going left or right, I'm just going up here. So wouldn't this be 0, 1? It's a y-intercept, isn't it? What about over here? What would this point be? Negative 1, 0. And this guy would be down here, 0, negative 1. Okay, so these are what we call special angles. And again, we're going to talk about those later. So in essence, anytime I rotate any amount of degrees, so for example, if I rotate 166 degrees, I would write that as the cosine of 166, and the sine of 166. So out of curiosity, what is the cosine of 166 degrees? What does that equal?
Negative 0.9703.
0 point, sorry, you said that. 0.03?
Yeah, 9703. Mm-hmm.
Okay, perfect. What's the sine of 166?
0.2420. No, sorry,
Okay.
2419.
2419? Okay. Thank you. Okay, so to get to this point right here, would you agree you have to go over a far distance left, so it's negative, and then you go up a short little distance? Well, which one would be farther over left? Wouldn't it be this guy? And then aren't you just going up a tiny bit, 0.24? So if I actually kind of just map this out for a second, if I want to go from this point over to this point, don't I go over far and up short? Over far to the left, negative, and up short. How are we doing? What about for this guy? What about for this guy down here, sine 257? Wouldn't I have to go over just a little bit, but I'd have to go down quite a distance to get to this point? So on your calculator, if you evaluate cosine 257, it should be smaller than the sine of 257. Can you please try that on your calculator? You can keep it in your display if you want, or you can write it down. What's the cosine of 257 degrees?
Negative 0.22450.
Yeah, sorry, this is in the way. Negative 0.2250. Perfect, thank you. And what's the sine of 257? Negative
0.9744.
Perfect, thank you. So would you agree I'm going over a short distance, but I have to go down a farther distance? That's why the sine's bigger. Okay? So all through you're working with sine and cosine, these are the kinds of answers that you were getting, and this is why you're getting them. For a rotation of 311, I would start here, and I would go all the way around to 311, which would be over here. So for this guy, it might be a little harder to tell. It looks like we're going over a short distance and down a farther distance. It looks like that. I could find out for sure by evaluating those. Are there any questions on that? It's just talking about where the rotations are ending up, which quadrant, what's positive, what's negative, and which one's smaller and which one's larger. So do I have to go over farther than I have to go up or down? Is it positive or negative? Okay. So, again, I don't know. I changed these. I can't tell you how many times I adjusted these and messed up again. Oh well. Did you ever wonder why anytime you calculate the value for theta, cosine, or sine, the answer would always be a value between -1 and 1? Does somebody have a question?
Yeah, I was wondering if the quadrants were going to be important for later questions.
Yes, yes. Yeah.
And is it important to know which quadrant is which?
Yes.
Okay.
Yeah. So if I just go back to this one for a second, Celine. If I'm going to name these, quadrant 1, quadrant 2, quadrant 3, and quadrant 4. That's an excellent question you asked.
Okay.
Okay? And when we rotate, this will become more important when we talk about the unit circle itself. This is just kind of getting acquainted with what's what. We always rotate counterclockwise. So if you have an analog watch, which I do, I'm old school, I don't use my phone, with the hands, we always go clockwise, so top to bottom, back to top. This time we rotate the other way. We go in a counterclockwise position. Just to confuse us more, right? Okay, so I gave you a little example here. For example, cosine 45 degrees, 0.7071, and the sine of 300 is negative 0.8660. So if you do this on your calculator, you should get the same answers as I did. Now, this is just kind of reiterating what we just did, looking at the angles we already used. If you do this, your answers are still between -1 and 1, depending on where they are on your circle. Okay, so x is always going to be between -1 and +1, and y is always going to be between -1 and +1, but including those values. The reason why we can include the values is because this point is on the circle, and if my radius is 1, it's 0, 1. This point is on my circle. Well, if this is the center, this would be 0, -1 right here. So I wrote over here at 0 degrees. So if I start right here at this first pink dot, right here at 1, 0, what's the cosine at 0? You can use your calculator to get this. So if I don't rotate anything at 0 degrees, what's the cosine?
1.
It is 1. What is the sine?
0.
0. Good. So if I rotate this way, if I go a quarter of 360 degrees, I think I'm going 90 degrees, aren't I? So now I'm up here. What's the cosine at 90 degrees? Zero?
Yeah.
And the sine at 90 degrees, it should be 1. So you can keep doing that with the special angles. You can try for 180, you can try for 270, and if you try 360, you should get the same as what you had when it was 0. All of those should be the same, okay? So we made a little note here, positive direction, negative direction. So we always go in the positive direction unless they tell us it's an angle measure of -30 degrees. Well, if positive 30 would go this way, because that's how we rotate around the circle normally, or if it said negative, I would go back 30 degrees. And again, we'll get into more of that when we look at some questions. All right. So what do those questions look like? From a unit circle diagram. Yes. Or is somebody trying to get in? Isaac, are you in?
Yeah.
Okay, perfect. Thank you. All right. So, cosine 270 and sine 270. Well, we can draw a little sketch of it. We can draw our circle. We can say we're starting here at 1, 0, because that's where we start every time. And we rotate 90 degrees, 180 degrees, down to 270 degrees. So I end up here. So I know that this is 0, -1. If I forget, can I just do it on my calculator? Cosine 270, can you check that please and make sure that you get 0? And the sine of 270, make sure you get -1. So the ones that we looked at on the X and Y axis, they're very special. All they are is variations of -1, +1, and 0. That's it. So at 180, if I start here at the red dot and I rotate counterclockwise 180 degrees, don't I end up right here? So the coordinates of that point from the center are -1, 0. Any questions on example 2? I think we only have one more example. Then we're finished. So, find the coordinates of P and Q. Well, here's P and Q right here. Round it to 3 decimal places. Okay, we look at P. We can use our little mapping rule. These are not special angles, so we're going to have to use our calculator. So P, I would say cosine 212 for X, and then to get Y, I would do sine. So this is X, and this is Y. So the coordinates of this point would be -0.848 and -0.530. I like 4 decimal places, by the way, as you know. So to get to this point, I have to go over a far distance, but I only have to go down not as far. Do you see that this length is longer than this length? That's why this number is a farther distance left than this is down. So normally we rotate positive. In point Q, it says -51. So we're actually starting here and we're rotating -51 degrees. We're going this way. So on your calculator, make sure that you put in the negative button. Okay, for that you have to use your negative key. And it gives us the approximate points for that guy. So I end up with, so to get here to this point, I have to go over and down. So 0.629, that's positive because I'm going to the right, and then I'm going down below the axis. -0.777. So these guys are not on the axis. These guys were on the axis. We had nice points here, just like I showed you back here. These are all really nice ones, your X and Y intercepts. These are not, so we have to use our calculator. Make sure your calculator, I put a little note over here, is in degree mode because you're asked to give your answers to 3 decimal places. It isn't the question in degrees. That's how you know. Okay, last little bit here. Consider the point P. So we have an X and a Y. Cosine is X, sine is Y. Where A is acute. What does acute mean?
Less than 90 degrees?
Yep. Perfect. So does this look like it's less than 90 degrees? I think so. So do you remember tangent is opposite over adjacent? Does that sound familiar from days gone by?
Yeah.
I feel like those were the easy olden days, weren't they? When we had simple things like that to remind ourselves of. Okay. So if I think of opposite over adjacent when I'm working here, what does that mean? Well, the opposite, if this is the angle, isn't the opposite side sine? And isn't the adjacent side cosine? So tangent can be defined as opposite over adjacent, but it can also be defined as opposite, which is sine theta over cosine theta. Isn't that the slope of the line? The rise over the run? So the tangent of an angle is equal to many things. Opposite over adjacent. It's equal to sine over cosine. It's the slope of the line that connects the point to the center. So we have a little poor tangent. We can't leave tangent out. We have all kinds of stuff going on for cosine and sine, but now we have something for tangent also. Okay, so how does tangent come up in a question, let's say? If I give you theta is 320 degrees, what quadrant would 320 degrees be in, by the way? 1, 2, 3, or 4?
4.
Yeah, because I'm going to go 90, 180, 270. It's in here somewhere. Okay. So if we draw a little picture, for 320 degrees, so let me get rid of this for a second. Put it back on if I need to. Okay. To go 320 degrees, I always start right here, and then I always rotate this way. So I go all the way around from here, all the way around to here. So it's in quadrant 4. The x coordinate is positive. The y value is going to be negative. Now, the tangent. Well, the tangent is going to be sine, so it's going to be negative y over positive x. So overall tangent of the angle should be negative. On your calculator, can you do tangent of 320 degrees and tell me what you get?
Negative 0.8391.
Yay, it's negative. Perfect. Okay, so I didn't even get sine and cosine yet. It didn't matter. I just wanted us to think about, well, what would tangent be? Well, I know that cosine is going to be positive, because to get to this point, don't I have to go over and down? So that's positive x and negative y. So it says determine which are positive or negative. So I think the x and y piece should be fairly easy and straightforward, but now we're adding in tangent. So tangent is always sine over cosine. So whatever signage sine and cosine have, that will dictate what tangent becomes. Okay? That's the only thing about tan that we really need to worry about at this time. Okay, so that's a big lesson today, 2 parts. Oops. Okay, so I put a note here for the videos because I want to put those up while you're working. The next slide is not slide 17. It's actually slide 19 now because I added something in. So I've given a unit circle here. It's a blank one. I'd like you to have a blank one for next class. So you can certainly print this one if you want. There's all kinds on the internet. So if I just go to the internet and I Google unit circle. Actually, if I do blank unit circle, that's printable. You get all kinds of them. Okay, so you might find one that you like a little bit better. It's completely up to you. But I would like you to have something, please, for next class, okay? So that, because we're going to be filling it in together and see where we are. If you don't have a printer at home, you can just take an object. You can take a mug. You can take anything, make a circle, mark off your quadrants based on one that you're looking at to make sure that you're okay. Okay, so for Thursday, we have these. that you can work on. And what I've done is I've posted all the solutions, I believe, all the work solutions here for 21A and 21B. So as you work through, you should check your answers for sure to make sure that you're doing things correctly. And if there's any that you're not understanding or not getting, I'll take those questions as you're working this morning, or as we get started there on Thursday. Let's get rid of that. Okay, so I'm just going to turn off the thing. Oh, I wasn't recording? But I was.